Mm. I'll start now. It's already late. I don't. Nobody has joined. Okay. So today we'll have a long, like a lot of things to cover. So let's start. So I'm Abhinav Chandrakar. I hope I'm audible. I'm Abhinav Chandrakar. I'm a PhD student at IC Bangalore, and I'll be the TA for this course, Mechanical Behavior of Materials, being hosted by NPTEL and being taught by Professor Sankaran from IIT Madras. This is the doubt and problem solving session for the contents of week 9 of this course. So let us start with it. We had not finished the week 8 content last time, so some of the portions pertaining to creep are still remaining. I'll firstly look at them and we'll look at the assignment questions related to them. Then we'll move on to week 9, which is on fracture mechanics. Just a minute, I'll take a important. Sorry, but I'll have to quickly go and finish some work. So since nobody is there, I think it is okay. I'll just go and get some things done, and I'll extend the session so that the recording will still be of the whole content. So for now, I'll just put it on pause and then continue later. Okay, let's resume. So last time we were covering creep, but some portion was left. We'll continue that part. We had looked at diffusion based creep, um, diffusion based creep and the equations which can describe them. Now we'll look at dislocation based creep, which is also called power law creep. The reason for it I'll tell in the subsequent portion. So dislocation based creep can occur multiple different mechanisms. So one of the mechanism can be that there are solute particles which are attached to the dislocation, so they are getting dragged as the dislocation is moving. Then we can have climb and glide base creep. So basically it is climb controlled glide creep, which involves dislocations undergoing climb to overcome obstacles, and then gliding on um, and then gliding on the new planes where they have climbed. So these are planes which do not have obstacles until they encounter another obstacle and again climb. So that is how it happens. And these have higher stress dependence than diffusional creep. So in diffusional creep, we had seen that the stress dependence is sigma raised to 1. And that also comes due to atomic volume related effect. But here we see that the dependence of stress on the strain rate is much higher. This is a general expression of strain rate of creep, and it depends on multiple factors such as sigma, grain size, temperature. So here we see that m dash is m dash is the stress exponent, and it will be quite high, maybe 3 to 5 for dislocation based creep, while it is only one, actually 0 for diffusion based creep. Here you have another term, sigma omega, which will be having some value, and it basically defines the mm, atomic volume in a way. Sir has taught that in his lectures. Hmm. And we know that for Nabarro herring creep and cobalt creep, n value will be for cobalt you have mm, grain boundary diffusion based creep. So the n value is about 3. In Nabarro herring, you have gray interior of grain also contributing to diffusion. So n value is 2. Then there are deformation mechanism maps, which are very important. They are the end product of these creep studies, which can tell you whether which kind of creep is expected to take place in a particular regime, which will based on the conditions such as temperature, stress, or grain size. These things. These are important. You can check that in slides. Ah. Now we'll come to some estimates of creep life, because it's important. This is important from a design perspective for industry as well as from lifetime prediction for components which are already in operation. So we can write our strain rate equation in this kind of form, and we can assume that at some value of strain, uh, the component has failed. You can call it rupture strain also, and we can denote it by K. So if you write K in this form, then you can plug this in the above equation and get this expression Lm equal to T into log Tf plus C. So basically this is also called the Lm parameter equation. Lm is the Lassen-Miller parameter, and this is basically the same previous two equations combined together, which tells you that the time to failure for a constant value of stress, the time to failure and temperature will have this kind of relationship, and there will be a constant involved called Lm, which will depend on the material. So this can be used for getting time to failure or rupture at lower temperatures where the creep strain is very low. But still you can make extrapolations using this equation and find out the time to failure for lower temperatures. Next, we'll look at creep in polymers. So polymers also undergo creep, and it's in a way mechanism wise different from what you see in metals, and the properties and stress versus time curve, strain rate versus time curve. These are also all different for polymers. We have seen earlier also that polymers have weak van der Waals interchain forces, and these are the bonds which later on will affect the deformation of the material. Along with the usual way, there is one more way of testing the polymers creep properties, and that is by stress relaxation. So, in stress relaxation, what you basically do is you make a material, apply a stress to a material, it will deform, and then slowly you just hold the material, so that hold the material such that your mm, strain is fixed, and that at that fixed strain you see how much stress is required to keep the material in place. What usually happens is that the material slowly relaxes due to plastic deformation creep happening over time, and the amount of stress that you need to apply slowly reduces. That is called stress relaxation. And for modeling these, we have mostly this polymers, but it applies to metals also. We have the spring dashpot model. Spring has this kind of a equation, F equal to Kx kind of equation, while a dashpot have more of a capacitor kind of equation, sigma equal to eta into d epsilon by dt. And so it has not been taught in the class, but uh, this can be compared to electrical circuits to quickly solve in order to quickly solve for certain arrangements of springs and dashpot. So since we already know how to solve for electrical circuits, we can just make an analogy of it the with the models we have involving spring and dashpot and these equations. And then after solving for these electrical circuits, you can replace it back with these. It's the same thing only. Physics is the same, just that it's for different entities. Hmm. Give me a minute. Hmm. Yeah. And using these string and dashpot, if you keep them in series, you call it a Maxwell model, and it predicts well stress relaxation phenomena. But if you keep in void and keep them in parallel, it's called void model, and it predicts well constant stress deformation. So each of these models predicts one phenomenon well, but it cannot predict the other one. This is also one of the aspects of this string dashpot approach. Then the polymer's creep resistance will be affected by the structure of it, just like in metals you have the microstructure and the composition. Here you also have the structure which comprises of the molecular weight and the degree of cross-linking and nature of cross-linking that is in the polymer. We have something called compliance modulus, which can be used for making some plots and doing better analysis, I feel. Also, we have this concept of master curve, sir has taught it, where you can use the some portions of time temperature curve, and by using some empirical methods or clever approach, try to get the curves for a for the mm, whole portion of so basically you can get the creep curves at different uh, temperatures and stresses by using just some portions of a known curve, and it's called a master curve. So this helps you to reduce the number of experiments you require to get your properties of the material. Similarly, you can also have stress relaxation modulus, sigma by epsilon naught. These modulus and master plots are useful for those who work on polymers and their creep resistance or plasticity. Then the last portion on creep is superelasticity. As the name says, superplasticity, sorry, as the name says, it refers to phenomena where material undergoes very uh, high amount of plastic. It can show high amount of plastic strain without failing. It could be maybe 5,000% or so. So that's a very high amount. So 1,000 to 5,000% is high. 10,000%. And even 500% is high. And this is usually seen as at high temperatures only. We can write this kind of equation to relate the stress applied to the strain rate, and here m is your strain rate sensitivity. We see that at for m equal to 0 the material is insensitive to strain rate, but m equal to 1 it's directly proportional. However, it has been observed that if the m value is more than 0.5, the material will typically show superplasticity. This happens because there is a resistance to the development of neck in the material. So as soon as the neck starts to develop, the strength of the material will increase a lot due to this strain rate, because the strain rate is reducing there. As a result, the further deformation will be at other places, and overall the deformation will be uniform. A lower grain size and higher temperature can help to um, have a higher value of M. Mm, so this facilitates superplasticity. One more way of understanding this is that of understanding why these conditions favor superplasticity is because it has been seen that um, superplasticity occurs majorly by grain boundary sliding. So through diffusional flow of material, mostly at the boundaries, and by this mechanism we can have superplasticity, and it is a competing mechanism with diffusion based as well as dislocation based creep. This can especially be applicable, I think, at high temperatures. Sorry, on the, of course, at high temperatures, but on the lower end because it requires lower volume transport and diffusion distance is lower compared to diffusional creep. So at lower temperatures, the diffusional creep might be slower, but superplasticity or grain boundary sliding may be more prominent. Mm. Mhm. Okay. And also the stress required for it is higher than that required for diffusional flow. Now let's go to the assignment for this and see the questions which were left pertaining to this content. So in Oro-1 creep model, where both dislocation, glide and climb take place due to combined effect of stress and temperature, which one of the these accommodates more amount of strain? So this is, I think, the same as the power law creep we saw, where we have rate controlling climb, but majority of strain occurs by glide because dislocation can move a larger volume by glide and much more easily compared to climb, which requires diffusion. So I think correct answer should be glide. Let's see the answer. Yeah. Then fifth question. In Oro-1 creep model, mentioned in question 4, which of the following is the rate controlling step? It is the atomic diffusion, because that is the mechanism involved in glide. Mm, then we have just one more question. There were some doubts in the previous question. We'll try to I'll try to see. I could not actually go through, like, could not address it till now. I'll maybe address it in the coming week. I'll try to study a bit about those and then see if the answer is still correct. Anyways, let's proceed. So last question is 12. You have two materials and LM parameter PA equal to this and PB equal to this. Which material would be stronger if CA less than CB and the curves of sigma and P coincide? So they have the same sigma versus P curves, only C and CB are different. P is Larsen-Miller parameter. Sigma is the stress applied for creep, constant stress. And we know LM parameter will be constant for a particular value of stress on load. So, so for let's say particular stress, PA and PB LM parameter, they will be the same. So we have CA plus this and CB plus this. Which material will be stronger has been asked. So basically, we can from this tell which material will have a longer life, right? So since both of these are same, PA equal to PB. No, 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 sorry, they are not the same. Sigma versus P is the same, but P is the Larsen parameter for A and PB is for B. So if CB is higher, it means for a given temperature, the time to rupture for B is lower, while that for A is higher. Since time to rupture is higher, for A is higher, mm, A will be more creep resistant, that we can say. But it is asked which would be stronger. Uh, it's difficult to say based on this. I think A is more creep resistant. If I had to choose stronger one, mm, let me think. So time will be more for A. So A has higher creep resistance, but let's see the answer what it is. A will be stronger. Maybe they refer to creep resistance when they say it will be stronger. And of course, if material is creep resistant, if it is not deforming so easily, it kind of means that it is stronger. It's probably due to high number of obstacles in the material, maybe some kind of boundaries in the material. So that also makes the material harder. So that way it is correct. Mm. Okay, so with this, this chapter was finished. We'll go to week 9 now. There are some portions of assignment 7 and 8 I know which I have not been able to get to till now. Like some which did not match with our answer key. But I'll post it in some time, share it in some time. And for now, let's start with week 9. Probably in the next session, I'll explain those week 7 and 8 doubt. Now we go to week 9, but before that, let's take a short break. Let me first just open up week 9. Let's take a short break and then we'll resume with week 9 content. Let me do one thing. I'll resume the session and anyways, there are no participants, so I'll resume it and then I'll upload the recordings. For now, I am signing out.